There we go. And now we're being recorded. So nothing that we covered at the beginning there I think was too critical. So thanks, Keith.
Oh, you bet. And just on another note, if you're looking for a gator, you can go no farther than Donna Beal. Donna Beal is a gator.
my wife's a gator too. So she always gets excited when she hears about other gators.
Okay. And Howard, of course, was a gator also.
Howard was a gator. Florida does sound quite nice right now. Okay, so just to kind of kick off, again, using kind of Keith's structure in terms of just showing you happy dopaminergic releasing thoughts at the beginning, at least for me. This is a picture of me reading to my son, but again, kind of marrying Keith's love for cats and my offspring. Here's a picture of me reading Cat's Colors to my child with our cat watching. And Cat's Colors is a book I've read so many times. We started to read it in Spanish now. So yeah, fun times there. But you know, that relates much to what we're talking about today. We'll be talking a lot about neurotransmitters, and again, as that, you know, that new forming brain has so much synaptic plasticity to it. Many of the neurotransmitters that we talk about today will be mediating that synaptic plasticity or that ever-changing and molding brain. Okay, so we left off talking about the major excitatory neurotransmitter, and today we're gonna kick off talking about the major inhibitory neurotransmitter. And so GABA is going to be one of the major inhibitory neurotransmitters. We'll talk about GABA and glycine. They both have inhibitory roles in the brain. GABA, however, probably has a little bit more of I would say a significant role as an inhibitory neurotransmitter. So if we look at GABA synthesis, again, this is very kind of similar to what we were looking at when we looked at glutamate synthesis, is that there are important enzymes that are essentially mediating the changes of GABA into its final form. So what's interesting about GABA synthesis is it actually is derived from glutamate. So you can see here that the GABA T is an enzyme that transanimates alpha ketoglutarate to form glutamate, and then can also inactivate GABA to semialdehyde. So you can see the role of that GABA T kind of in the back parts of the GABA synthesis. But GAD T is going to form GABA from glutamate. So if we kind of, this step 2 that you see here in this figure on the below, that's where you're going to see GAD actually acting to form glutamate, GABA from glutamate. And so if GAD, that enzyme, is present in a neuron, it's generally considered an interneuron because it is an inhibitory neuron. And so when we talk about the different types of neurons, you know, glutamatergic neurons are going to be excitatory, GABAergic neurons are going to be inhibitory, and they're often called interneurons. And so I combined this, I guess, cycle down here with the synapse that you can see here. You can see, again, the role of GABA T as well as GAD, showing how it derives GABA. And then the next figure, we're actually going to go through all the steps in kind of the GABA cycle here. But again, these are just some important enzymes required for the synthesis of GABA. And somebody has already given me the feedback to slow down. So at any point, feel free to just give me that and I'll make sure I'm talking my way through these slides a little bit slower. Again, I want to make sure you're getting all of this information. So kind of moving on from GABA synthesis to the GABA cycle, many of these neurotransmitters, I've tried to structure these slides very similarly. So if you're putting together a table, or again, I think when you're learning a lot of different things, having a similar structure is helpful because then you can do kind of a compare and contrast between those systems. And so many of these slides are going to be set up with what happens in the presynaptic side, what happens in the postsynaptic side, and then what happens for termination. And so presynaptic side would basically be how is the presynaptic vesicle loaded? Is there a transporter involved, and how does that happen? Postsynaptic would be post release of the neurotransmitter. What postsynaptic receptors is it going to diffuse and bind to? And then lastly, termination would be what type of terminating process occurs for that particular neurotransmitter. Is it via enzymatic action like we see with acetylcholine, or is it via transport mechanism like we saw with glutamate? So again, I tried to make that structure very similar for some of the more in-depth neurotransmitters that we talked about, or that Goodman and Gilman talk about in this particular chapter. So the presynaptic side, GABA is located into vesicles via VGAT. So you can see that VGAT transporter there. Again, it's going to take a low extracellular concentration, or I should say intracellular concentration, to a higher vesicle concentration, and so VGAT's going to work in that manner. Once the interneuron is stimulated and synaptic release occurs, you can see here that it diffuses across the synaptic cleft and binds to either GABA A or GABA B receptors. GABA A and GABA B, similar to what we saw with glutamate, these neurotransmitter systems often have an ionotropic and a metabotropic version of their receptors, and GABA is essentially the same type of system. And again, that gives the brain a lot of really interesting modulatory effects, you know, where you have the fast neurotransmission being mediated by your ionotropic receptor and you're slower by the metabotropic. And so it's just another way in which the brain can kind of modulate its response. But as you can see here, the GABA A receptor is going to be your ionotropic receptor, and it's going to be permeable to chloride. And again, that kind of lends to that inhibitory action of GABA release. It binds to the receptor, causes a conformational change, the channel opens, and then because of that driving force of chloride's going to flux into that postsynaptic cell, and it's going to cause a hyperpolarization or kind of a negative decrease in the resting potential of that cell, causing it far less likely to depolarize. So that's how it has that inhibitory effect on the cell. It's making it more negative, therefore more difficult for a action potential to arise because it's sitting at a negative resting state. You can see here that GABA B is the metabotropic form of the GABA receptor, and that there's going, not surprisingly, it's a G protein coupled receptor coupled to G proteins that are going to activate secondary messenger systems and affect things like calcium and potassium conductances as well. So you can see some of the postsynaptic effects of the GABA. And we're going to talk a little bit more about these receptors in following slides. So if you didn't catch everything I just said, don't worry, you're going to see it in the next slide or two. And lastly, the termination of this cycle is going to be via 4 GATs on neurons in glia that act as neurotransmitters. So here you can see the GAT1 and GAT2 expressed on the neuron. These are going to be the transport systems that uptake that excess release of neurotransmitter. And just recognize that the placement of these are not arbitrary. GAT1 is going to be expressed within the synapse, and GAT2 is going to be expressed what they call perisynaptically on the presynaptic terminal. And so perisynaptically is just, again, kind of right outside of the synaptic cleft, and then that GAT1 is right there at the cleft itself. So if we break down these 2 different types of receptor types for GABA, again, the primary inhibitory neurotransmitter for the CNS, you can see that GABA A, again, as I said in the last slide, is ionotropic. It's permeable to calcium. It's pentameric. It's got those 5 subunits, 2 alpha, 2 beta, 1 gamma. Calcium, or sorry, not calcium, chloride selective. That's going to cause that negative influx or that hyperpolarization, and can be inhibited by bicuculin or picrotoxin. Those are going to be the 2 inhibitory antagonists that you'll see. So here, if we look at the GABA A structure of the receptor, you can see that you have a competitive antagonist of bicuculin because it competes for that GABA binding site. But then for the benzodiazepine site, you have irreversible agonists that can bind there as well as antagonists. In terms of the picrotoxin site, you can see that's located far more deep in the pore, and it's not competing for the GABA binding site, so it's a non-competitive antagonist. It's just, again, just worth noting that there are other binding sites here that are modulatory and are bound by pharmacological agents that you might see in the clinic, things like barbiturates and steroids. Now, when we get to, we'll probably talk about this a little bit more when we get to speaking in depth about the GABA receptor, but again, this is just kind of a general overview. The GABA B receptor, again, is metabotropic, and there are going to have, what is it? Inverse agonist. An inverse agonist, the inverse agonist. Oh, so the inverse agonist is going to mitigate the stimulation via an agonist. And so you can see here that there is an inverse agonist binding site. And Keith, do you want to describe an inverse agonist, just because I feel like my description might not be completely.
Yeah, Katie, thanks for the question. It's a good question. We haven't really talked about inverse agonists yet, and I'll jump into my historical mode here for a moment. Inverse agonist is a relatively new concept in pharmacology. When I was in graduate school there ages ago, the concept was unknown. Uh, Antagonists, full antagonists basically have what we call zero intrinsic activity, in that they don't turn that receptor on one way or the other. Agonists have intrinsic activity and they turn receptors on in the direction that we quote unquote expect them to be turned on to. Inverse agonists have an opposite effect to regular agonists. So, for example, I'll just take it outside this realm. If you were expecting an agonist to produce increased concentrations of cyclic AMP in the cell, an inverse agonist would have that opposite effect and would produce decreased concentrations of cyclic AMP. So it's broadened our perspective quite a bit about drug action to have this concept of inverse agonist. And it's a very important concept in the realm of sedative hypnotic drugs, such as the benzodiazepines. And a further thing that I'll throw in at this point is that, as Katie pointed out, there are these multiple binding sites on these receptors, and this turns out to be super important stuff when we get into the sedative hypnotic drugs and some other categories. So this is a very, very important concept. And as Katie said, we'll be coming back to it later in the course in more detail for sure. Does that help out enough?
Yeah, and so the follow-up question for that was, does it change conformation unlike an antagonist? And the answer to that would be yes.
Yes.
Yeah. Keith, would you characterize that as a negative allosteric modulator then?
I think you could, yes.
Okay. Yeah, just because I think for me personally, watching the field of pharmacology evolve, I think positive and negative allosteric modulators are going to become kind of a huge therapeutic field in the future, just because you're basically taking intrinsic activity and kind of turning it up and turning it down. At least that's kind of my viewpoint. I don't know if you feel differently, Keith.
No, I think that's a very refreshing perspective on it there. Just right on. So anyway, from a student standpoint, I know this is a new concept, so it may be a little bit confusing for a while, but it's kind of one of those buckle up your seatbelt a little bit and hold on, because we will be exploring the concept of inverse agonism more just in a short period of time in the course.
Yeah, but I think that maybe that would be kind of a fun jumping off point for Tuesday's lectures, just to talk about the different kind of characterizations of pharmacological agents and like the different ways in which they bind to receptors and can modulate them. Have we done kind of a encapsulate? I guess. Did you think we covered
just
that?
a little bit in the context of agonists and antagonists, but not as far as this one. You're right. You can explore that more next week. And one other way to think about this a little bit is if you use sort of an activity line with the names of agonist, antagonist, and inverse agonist on that activity line. In the old way of thinking about it when I was learning about this stuff was that antagonism and agonism were sort of on the opposite ends of that spectrum. Now, the opposite ends of the spectrum are the inverse agonists on one hand and the regular agonists on the other hand, with antagonists sort of in the middle. Mm-hmm. And so zero would be in the middle, and then you would go minus or plus from that. So that's another way to sort of think about inverse agonism a little bit.
Yeah, I think even just getting all of that terminology, just I think on a single slide could be really valuable, and even creating a figure that you're describing, and even kind of incorporating even blockers in there, because blockers are kind of different in what they do than antagonists as well.
That'll be great.
So there's a question about the use of toxins for classification that popped up here. In terms of toxins as being as kind of for classification purposes, I kind of alluded to the fact that they have a high kind of evolutionary value to them. Again, the animals that are secreting these toxins are intentionally secreting them to bind to specific receptors, and so that they've essentially created some type of chemical that will be secreted that will render, you know, predator or prey or what have you immobile in many cases, or create some type of central nervous system dysfunction, enabling them to either escape or to take advantage of their prey. And these toxins essentially are incredibly high affinity to specific receptors or transporters or whatever kind of or ion channels that we're talking about. And so pharmacologists and neuroscientists have essentially identified these toxins as having these super high affinities for these receptors. One example actually that I've worked with personally is botulinum neurotoxin. It's actually the most potent neurotoxin known to man. Just if a liter bottle could render, you know, the entire East Coast just paralyzed, and could paralyze everyone's diaphragm. Anyway, again, it's just that idea of using a toxin that binds very specifically to a site to characterize either the receptors or ion channels that they're binding to. For the person who asked me that question, just go ahead and let me know if that answered your question, or please feel free to send me kind of a follow-up question to make sure I do go ahead and clarify whatever your question might be. Okay, so again, this is, I think, a great image, and we've seen a couple different receptor images showing different binding sites in the fact that you do have an agonist-antagonist binding site. And I alluded to this idea of positive and negative allosteric modulators, which I'll include in kind of the introductory slide for Tuesday, because I think that would be really helpful. For GABA B receptors, those are the metabotropic receptors. They mediate the slow, relatively fast still, but slow neurotransmission of the interneurons. They're composed of heterodimers, meaning there's two subunits that are different in composition. They're alpha-I coupled and either inhibit calcium or activate potassium channels. And again, if we think about what the downstream effects of those are, inhibiting calcium could have, you know, an inhibitory effect to any possibly type of plasticity that's occurring. If we go back and we think about calcium influx in postsynaptic cells when we were talking about glutamate receptors, that influx of calcium actually caused a potentiation or essentially the increased formation of synaptic strength between those two cells, and so decreasing the amount of calcium is going to have the opposite effect. Or activating potassium channels. Potassium channels, as we remember, are positively charged ions that are located inside the cell. So if you're activating those potassium channels, you have potassium leaving the cell, and again, you're having a positive ion leaving the cell, which is rendering the cell more negative. So it kind of achieves that same hyperpolarization state that the ionotropic GABA A receptor does. It's found in perisynaptic regions and activated by GABA A spillover. So when GABA is released into the synapse, you have obviously transporters that are trying to reuptake that neurotransmitter, but some of it does escape that synapse. And so when it does, it hits those perisynaptic regions of the neuron. And so this is where you're going to see activation of these particular types of receptors. GABA spillover occurs in cells, glutamate spillover occurs in cells. Generally what happens in those spillover types of situations is that you have different receptor subtypes that get activated, and that kind of allows the cell to respond in a slightly different way than if it was just being activated in the synaptic cleft itself. Let's see, agonists for this, for GABA B would be baclofen, which acts as a muscle relaxant, or GHB, which is a psychoactive drug, which we will talk about psychoactive drugs in one of our later lectures. Okay. So just to kind of draw off of the further from this particular figure, you can see these GABA A receptors have these different agonists or antagonists that are binding to it, as you see on the figure. That's kind of the same list you see here over to the left: the benzodiazepines, barbiturates, ethanol, analgesic steroids, and then you can see some of the disorders that they're used to treat. So we see them used for neuropsychiatric disorders, epilepsy, Huntington's, addictions, and sleep disorders. So in disorders where you maybe see an overactivity of the brain, this is often kind of one of the targets for that. That's why things like epilepsies and seizures, you often see GABA being prescribed, GABA agonists being prescribed, because you want to kind of dampen down that overexcitation of the brain, so that overexcitation can be mitigated by actually treating with a type of GABA. Okay, so next inhibitory neurotransmitter we'll talk about here is glycine. And I shouldn't even admit to what I did. I was like, I'm going to throw this up here and have them freak out about learning this pathway. You do not need to learn this pathway. I basically just want you to focus in here on the serine to glycine part of the synthesis pathway, and this SHMT that causes the change of the transformation of serine to glycine. So this is really all you need to be focused on here. But you'll also recognize there are some other players in this whole system that maybe we've seen before. Okay, actually. Well, we're just gonna delete that. Okay, so in terms of glycine, like you saw that previous kind of image, is that it's essentially made from serine via this SHMT, serine hydroxyl methyltransferase. Again, using that very similar structure of synthesis, presynaptic, it's imported to the vesicles via VGAT, and upon release, it binds to NMDA receptors. It's a co agonist for NMDA receptors, and can lead to a hyperpolarizing chloride efflux as well. For postsynaptic or reuptake, it has to reuptake through the GLT1 transporters and GL1T2. The antagonist would be strychnine, and then the agonist taurine and beta-alanine. Glycine is kind of ubiquitous. When I was studying NMDA receptors, I used to have the conversation with my PI, do I need to add glycine to our ACSF? And he's like, no, glycine is kind of everywhere. So you didn't have to worry about adding it specifically to our artificial cerebrospinal fluid, because it's a kind of ubiquitous protein or amino acid. Okay, so I've been chatting for a while, so we're going to go ahead and do one of our concept checks. So I'm going to go ahead and just pause here for a second. Hopefully you can take a nice deep breath in and go ahead and read through this concept check. And breakout rooms weren't a huge hit yesterday, so I'm going to go ahead and do what we did at the end of class yesterday and have you go ahead and privately messenger me once you've read this over what the cellular mechanism for this particular drug is. Okay. So, okay. So it looks like quite a few of you have come up with the right answer. So yeah, so the cellular mechanism for this particular drug, lorazepam, is it's going to be an agonist for the GABA A receptor. It's going to bind to that benzodiazepine site. So it's going to kind of, again, all of these different symptoms that you're seeing here kind of align with that idea of GABA A receptor being activated. Okay. So many of you kind of gave that answer and even expanded past that, talking about the influx of chloride, which I think is a great kind of next step, really thinking about the cellular mechanism of how chloride's influxing to the cell, causing it to become, harder to activate or depolarize and inhibiting neurotransmission. Okay, so any questions about this concept check for anyone?
Yeah, I was wondering, so why is her eyes not affected by it? Because I mean, they seem to be responding quickly and not as lethargic if the pupils are reactive. Is it just because of the ocular being like having their own network almost and how fast they are?
Yeah, so there's a different receptor system that's going to be responsible for that response.
I also think they're really trying to make the point that it's not an opioid. As you notice, naloxone doesn't do anything. And if there was opioid stuff going on, there'd be effects on the pupils, to be sure. Very likely, anyway.
Gotcha. And then it was saying after a night on the town, so does that mean she's mixing it with alcohol?
Sounds like it to me.
Yeah. Which is a whole nother conversation that we're actually going to have when we discuss alcohols on Tuesday and Wednesday of next week as well. Okay. Any other questions before we move on? Thank you so much for speaking up and asking questions. It always makes me happy when I hear voices coming out of the big black void. Okay. So kind of moving on from, we talked about kind of the point-to-point synaptic transmission that occurs in in the neurotransmitter systems of both glutamate and GABA as well as glycine. Here, we're going to kind of take a turn into neuromodulatory neurotransmitter systems. And so we'll be talking about dopamine, norepinephrine, serotonin, and acetylcholine. And you can see here kind of the way in which those neurotransmitters are released. It's not necessarily as much of a point-to-point neurotransmission. Some of these releases are considered to be kind of fall under the category of volume transmission. So they have far more neuromodulatory effects on the existing synaptic transmission that's going on. Now, the next slide is just something that helps me kind of think about these is when I think about the brain, I often think about, glutamate and GABA doing the excitatory inhibitory part of it. And then the other neurotransmitters having these very specific neuromodulatory effects. And so I always thought of the stereo that I saw growing up, which was basically, almost like a mixing board where you have, you either are stopping or playing, which would be like glutamate and GABA. And then you have all of these different things that you can change about the sound that's being created. And each one of those is a very, delicate dial, either dialing up or dialing down or changing that sound in a very specific way. And that's kind of how I think of the neuromodulatory drugs. They're kind of tuning the brain to have these specific types of signaling outcomes. And again, this is just the way I think about the brain. I'm sure there are different kind of thoughts or interpretations about it, but that's just, again, one kind of visual that I think of. So the first kind of neuromodulatory drug that we're going to talk about is acetylcholine. So acetylcholine was one of the first neurotransmitters characterized just because it has action at both in the peripheral and the central nervous system. For all intents and purposes, today we'll probably just be focused on the central nervous system, cell subtypes and functions. But because of that peripheral action, it was first characterized, I think, in heart. So the synthesis of this occurs via choline acetyltransferase. So you can see here in this wonderful picture of a synapse, you can see the acetyl coenzyme A plus choline and the formation of acetylcholine via the action of choline acetyltransferase. In terms of presynaptic loading of vesicles, you can see that that's done via VAT You can see here the vesicular acetylcholine transporter is going to be loading that acetylcholine into that presynaptic terminal, into that vesicle. And then once the cell undergoes activation and active potential travels down, influx of calcium occurs, and then exocytosis of neurotransmitter. And then once that neurotransmitter is released into the synaptic cleft, it's going to bind to postsynaptic receptors, either ionotropic nicotinic receptors or metabotropic muscarinic receptors. And so we'll talk about both of those different receptor subtypes as well. In terms of termination, this is slightly different versus the mechanisms that we've seen in the past. You can see here that termination is via acetylcholinesterase, which Keith talked about pretty extensively a few lectures ago, and some of the inhibitors that inhibit acetylcholinesterase activity. And so hopefully a lot of this should be kind of review for you, because we did cover some muscarinic and nicotinic material in the past. But this kind of, I think, is a nice slide, just kind of bringing together the whole system and showing you exactly how it's synthesized, how it's loaded into vesicles, how it's released, and then also postsynaptic receptors it binds as well, and finally the termination of that signal via acetylcholinesterase. Okay, so again, we're going to be talking about muscarinic and nicotinic receptors. This is just another really nice table that's included in Goodman and Gilman, just kind of bringing together a bunch of information and putting it right in front of you, showing you kind of a comparison side by side of what each of these muscarinic receptors kind of binds, is bound by, as well as the G proteins that are coupled to them. So there are 5 different muscarinic receptor subtypes, and you can see here the different G proteins that they are coupled to. You can also group this kind of into groups as well. You have your G-alpha Q in M1, M3, and M5, and then M2 and M4 are going to be coupled to I and O. And again, because of that G protein coupling, it's going to affect the downstream secondary and messengering systems that they're activating. You can see here, again, just examples of both agonists and antagonists. Not surprisingly, acetylcholine is going to be an agonist for all of these, first and foremost, but then you've got some non-specific agonists, things like carbachol will non-specifically activate all of the muscarinic receptors, as well as oxytrimone. And then you can see some of the other subtypes here, the M1, the M3, and the M5 are all activated via pilocarpine. So again, if you wanted to increase G-alpha Q activity via muscarinic receptor, applying pilocarpine might be the best way to do that. And lastly, here you can see just some of the antagonists that are going to block activity of the muscarinic receptor. And we're not necessarily going to go through all of those, but you know, as I keep saying, as an electrophysiologist, as a pharmacologist, you should think of how you can use these to kind of determine the underlying mechanism. And if you are, let's say, hypothesizing that, you know, M1 has a very important role in some type of cellular mechanism, using these agonists and antagonists can be really helpful for that purpose. And I put at the bottom there to see muscarinic lectures, because we have covered some of this material in the past. Next, we're going to kind of take a turn into the monoamines, talking about dopamine, norepinephrine, epinephrine, histamine, serotonin, and some of the trace amines. These monoamines, not shockingly, as we kind of alluded to yesterday, we brought up the idea of the SSRIs, play a very important role in emotion and are modulated quite frequently for cognitive disorders. Targeted to treat depression, schizophrenia, and anxiety. And again, many of the monoamines are just neuromodulatory in their nature. So dopamine is, you could probably have an entire lecture about the role that dopamine plays in the brain and the role that dopamine plays in motivation. I think there even could be an argument made that our entire lives and many of our choices are just ruled by dopamine and that positive reinforcement that it kind of occurs with dopamine release. So because of that, dopamine is also one of the targets of many drugs of abuse. Again, your brain is getting flooded with this very, you know, happy neuromodulatory neurotransmitter, and so often individuals kind of, you know, chase that high. There are 5 different GPR subtypes in 2 groups. So you have D1 and D2 like receptors, and you can kind of see their subgroups here. And you can also see the different G proteins in which they're coupled to, the GS, as well as the GI and the GO. In terms of kind of the more clinical side to dopamine, it has been shown to have some role in schizophrenia and Parkinson's disease. And so in some ways they've been, it's been a source of therapeutic targets as well. Okay, so next kind of going through the monoamines, we have norepinephrine. It's going to bind to the endogenous alpha and beta adrenergic receptors, kind of having different responses to each. So it's found in the hypothalamus and is going to be projecting and sending signals to both the amygdala, which is important for fear, and the dentate gyrus of the hippocampus. Again, the hippocampus is going to be an area important for learning and memory. What's interesting to note about the adrenergic receptors, at least, is that the alpha-1 is depolarizing and the alpha-2 is depolarizing. So you almost have these differences in effect that occur in the two different directions. And then if we look at alpha-2, alpha-3, and the beta adrenergic here, you can see the subtypes as well as the G proteins that they're coupled to for the secondary messengering systems. And then essentially the agonists and antagonists that are responsible for activating or blocking the action of each. Again, this is a very kind of cursory introduction to these neurotransmitters. We will be talking about them far more in depth as we go through the semester, but this is just kind of a general introduction to all of these. I'm going to pause for a second. Does anybody have any questions about anything we've covered thus far? I guess somebody did pop up a question. You need to know all the examples of both agonists and antagonists for each muscarinic receptor. I would say most often these agonists and antagonists are listed by almost the degree of affinity or their general usage in the field. So I would say like memorize at least maybe like an example of an agonist and antagonist. Probably the first one listed again is usually the one that's the most commonly used in the field. So I'm not going to ask you, you know, every single one of these, but I would say at least the first kind of one in the list is, again, it's usually the most commonly used for these types of characterizations. Okay, so kind of continuing to move, the epinephrine is just another neurotransmitter that is contained in the vascular elements. So I also included this image just showing you where the reticular formation, this is going to be the source of these neurons that are going to project to different regions of the brain for release. And kind of the interesting thing about epinephrine is in the CNS, their physiological properties are not entirely characterized, which makes them kind of a fun source of ongoing research currently. Next, we'll talk about histamine. So histamine, we're discussing a couple different brain regions here, and so histamine is located in the ventral posterior hypothalamus. Histamine, not shockingly, is involved in arousal, so if you could think of antihistamines and kind of the effects that they have, they also alter body temperature and vascular dynamics. So there are 4 different GPR subtypes that you can see here in this image, so H1, H2, H3, and H4. And again, they're differently coupled to different G proteins and thus having different downstream effects. What's nice about this particular image is that it shows you kind of the positive or negative effects that each of these G proteins is having on things like adenyl cyclase. And if you've taken a biochemistry class and had to learn these pathways, these signaling pathways, I'm guessing you're probably having a little PTSD now, but it's important, again, you learn these pathways for a reason because it shows you kind of some of the downstream effects that the things like adenylate cyclase has, where you can have these long-term gene responses that occur within those cells. What's interesting to note here is that H1 kind of operates via a slightly different mechanism. It's going to activate phospholipase C, and so increasing downstream PKC activity. So these secondary modulatory systems, what's nice is if you recognize what the G protein is coupled to and you have memorized the downstream effects of these G proteins, you can kind of start to see what the result of the activation of these different types of receptors are. I included on this slide just some interesting research observations that have been made for histamine receptors. So things like the H1 knockout mouse has affected sleep-wake cycle. So that means these mice essentially have the gene for H1 deleted from their system. And because of that, you see this type of response in those mice, the affected sleep-wake cycle. H2 knockouts has impaired cognitive effects and impaired LTP. So when you have a knockout mice that kind of had these downstream exhibited effects, it almost makes you want to go back and mechanistically understand exactly where these receptors are having these effects and where they're being activated to cause these kind of phenotypic changes. The transporter system for histamine is NetNOC3, and it's interesting to just note that in the PNS you've got degradation of histamine via histamine 3 methyltransferase, and that particular enzyme is lacking in the CNS. So instead you see these transport mechanisms taking place instead. Okay, so we're gonna, I think, probably wrap up with this last concept check. And so again, this is just asking about the role of antihistamine medications and what's the pharmacological basis for a switch. So I'm, as much as maybe people didn't enjoy breakout rooms last time, I'm gonna go ahead and send you into a breakout room for about 2 minutes here so you can have this discussion. And then I'll bring you back and we'll discuss it really quick here for the last minute or so of class. How are you doing, Keith?
Hanging in there, Katie. Thank you.
Is there anything that you would like to add or expand upon as I'm going through these neurotransmitter systems?
Just to reiterate what you've already said, and that this is a broad overview on these neurotransmitters and systems, and in every single case, we'll be going back to it at some time during the semester and developing the concept in greater detail. So sometimes at this point, it's a little bit overwhelming to look at all these different things, but rest assured that we will return to it and address it again and in a discrete fashion as we go along. So perhaps everybody can take that to heart.
Yeah, it's probably a little overwhelming right now. The students are actually all in breakout rooms. I'm going to bring them back after, because they've been discussing this case study.
Sure.
Okay. So, hi.
Hi, did you guys come up with your answer?
For the first part, I guess,
Okay.
it says it acts as an inverse agonist for the H1 receptor that diphenhydramine does.
Mm-hmm. Okay. And then has anybody found the hexoaphididine?
What was the question on that one?
Oh, yeah, you guys can't see this. My goodness. Okay, that's like the downside to this. The second question was, what is the pharmacological basis of switching to fexofenadine? Okay. I'm going to go ahead and bring everybody back to the main room, and then we can kind of discuss it as a group.
All right.
Okay.
Hey, Katie, it's already 1:50, so people were kind of getting stressed because it's time to go.
Oh, okay, that's fine. We'll go ahead and let everyone go right now, and this will be kind of the place that we kick off when we meet next Tuesday. So I appreciate everyone's time, and I apologize for kind of going a little bit longer today, But if you have any questions or concerns, do feel free to reach out and let me know. Be happy to answer those individually. And we'll wrap up our discussion of the CNS on Tuesday and then start our discussion on alcohols as well. So everyone have a great day, and we'll answer that question collectively on Tuesday.
Thank you.
Thanks.
Thank you.
So I had a question about, to clarify on inverse antagonists. If you had a minute.
Yeah, of course.
Okay, so my understanding is that when something binds to a cell, it creates an effect because that's what that receptor is meant to do. So how does an inverse agonist create the opposite effect without being an antagonist? You know, how does it change what the cell does?
So, I mean, I'll start answering this, Keith, and please feel free to jump in. So an antagonist is going to block the initial, whatever the conformational change. So if you have a conformational change and a specific ion is supposed to flux into the cell, an antagonist is going to block that conformational change from happening, even in the presence of an agonist. And an inverse agonist is going to cause an opposite effect. So I don't know if in that case, you would possibly have a conformational change that would, instead of causing an influx, would cause an efflux. Is that, you think, fair to say, Keith?
Yeah, and it's interesting to note that to classify something as an inverse agonist, you have to actually be looking for that opposite response. And in the early days of receptor stuff, people weren't looking for that response. And so a lot of things that were, originally classified as antagonists have now been reclassified as inverse agonists because you're actually looking for that opposite effect. So there's a bit of reshuffling going on in terms of classification of these various substances. I don't know if that's relevant to the question or not, but
Okay, yeah, I guess I just didn't think that you could change the conformation and still get a response in a way it wasn't meant to change.
yeah, the informational content of inverse agonists and full agonists and so on is different. So the message that's being delivered to the cell following binding is in a molecular and informationally based sense different for inverse agonists compared to the other compounds.
Okay, thank you.
Yeah, and Rebecca, I think on Monday, like I said, I'll put together a slide kind of comparing and contrasting all of these different terminologies we're using and come up with like kind of a specific example for each. And I think especially with an aided visual, I think it could kind of maybe come to life a little bit more. So I would say if you're willing to hold off until Tuesday, hopefully things will become a little bit clearer then too.
Perfect, thank you.
Yeah.
Have a good night.
You too. Thank you so much, Keith.